Hi everybody, it's Mr. Hamilton here and welcome to this lesson on section 3.3, Newton's second law of motion. If you're in my class, you should have this note printed out and be filling it in as we go through this. Let's begin today by looking at this next time question. It says, note the readings on the scales. Burl the painter has a weight of 600 newtons. Remember, weight is newtons, mass is in kilograms. And he carries a 100 Newton bucket of paint. What is the weight of the scaffold? Now you see there that we have 700 newtons on this spring scale and 500 newtons on that spring scale. Pause the video, take a moment, think about it, and then remind yourself as well, does it mean that the sum of the forces is equal to 0? That was what we learned in Newton's first law. All right, so hopefully you've had a chance to think this through. If 600 newton and 100 newtons adds to 700 newtons, then the entire mass of him, the bucket, and the scaffold is 1,200 newtons based on the two spring scales, which means that the scaffold itself must be 500 newtons. So here's the answer that Paul Hewitt has on his. But it says essentially the same thing I just said. We'll pause the video and read through that if you need to. All right, 500 newtons. Hopefully that's a pretty good understanding. With that in mind, let's walk through this handout together. We have three goals today. The first one is to state Newton's second law in words. Then we want to define force in terms of mass and acceleration. And we want to solve problems involving these three things: mass, acceleration, and net force. So the first thing to note is this. We're going to consider a hockey puck. Because of the simplicity of its motion, consider a hockey puck of mass 0.170 kilograms with a stick exerting a force to the right on it. So here's a puck. There's a hockey puck. We have a stick exerting a force on that hockey puck. And that force is going to go to the right. If an unbalanced force, so that's a net force, if some net external force or unbalanced net force, those things mean the same thing. There's a total force that's not zero. If an unbalanced net force acts on the puck will accelerate in the direction of its force. So we're going to draw a free body diagram of the puck with this net unbalanced force. So we have a normal force acting to keep it from falling through the ground that is equal and opposite to the force of gravity. So those are equal in magnitude, opposite in direction. Then we have some applied force that's pushing this puck forwards. And then we have a very small force of friction that's opposing the force. On ice, there's very little friction, but nonetheless, it is there. So in terms of vertically, we know the net force is 0, but in terms of horizontally, we know the net force is not 0. So the net force overall is the sum of the applied force and the force of friction, where if you say this direction is positive, then we're going to get a positive value for the applied force and a negative value for the frictional force. In other words, we're going to subtract the force of friction from the applied force. If the mass is constant, then if we measure the net unbalanced force, F net, versus the acceleration, we can see that this is a linear relationship. Linear relationship. So we can see this on the graph below. I've done an experiment, and I'll walk you through the different values of how I got them. The first value that I had was, I said, if I exert a net force of 0.06 newtons, then my acceleration was somewhere around 0.35 meters per second squared, because net force is on the y-axis, and I have acceleration on the x-axis. Then if we were to exert a bit larger force of about 0.125, we exert that force and we find that has an acceleration of just over 0.7 meters per second squared. And then if we do get data a third time, we have a net force of almost 0.2 newtons, and we find out that that makes the object accelerate at about just less than 1.1 meters per second squared. So we take those 3 points, we plot those 3 points, and then before we draw the line of best fit, we also say that it makes sense that if I have no net force, then I can't accelerate. So that also has to be a point at 0, 0. And so we then take that and we draw our line of best fit through those 4 points. And that line of best fit comes out with an equation, y equals 0.17 times x, where the slope is 0.170. Pause for a second. What number does that look familiar to? Look higher up on your handout. So how can this slope actually be the mass of the puck? Well, that's what we're going to investigate as we look in this idea of proportionality. So what we notice from the graph is as the net force acting on the puck was increased, the acceleration of the puck increased proportionally. Well, what does this idea of proportional mean? So we're saying that acceleration is proportional to the net force. One way to think of it is that when we graph the one versus the other, it gives us a linear relationship. But another way to think of this word proportional to is that as the net force increases, the acceleration increases or decreases. That would also mean proportional to. Could decrease as well, but in this case it's going to increase at the same rate, causing this slope to be formed that's a constant slope. So in this case, acceleration is proportional to F net, and there's one thing we kept constant. That was the mass. The mass is constant. The mass never changed of this puck. And so if we look at the slope of this graph, let's look at this. The slope is equal to the net force divided by the acceleration, the rise over the run, right? So this is the rise, this is the run. Well, what was the net force? Well, the net force, if you think about it, the net force is divided by acceleration. That means the slope, which we found to be the mass of the puck, is the m, is the mass. This is how we get Newton's second law. This is the equation that represents his law. We're going to rearrange this equation and do some math around this today, and we're going to put some vectors, obviously, on the net force and the acceleration, but we're going to just see how this rearranges and how this works out. Now, if we had done another experiment in which we kept the net force constant and compared mass versus acceleration, what we would find in that case is that acceleration is proportional to 1 over the mass. And that is only when the force, when the net force is constant. We're not changing that net force. Well, what does this all mean? Well, it means, look down at these two equations before I introduce Newton's second law, it means that acceleration is proportional to 1 over the mass. So one way to write that would be say area is proportional to 1 over the mass, and the proportionality constant, in other words, the value that makes it go from a proportionality to an equal sign, is F net, subbing F net in here. And likewise, I could talk about this over here in terms of F net is proportional to acceleration, and the proportionality constant that would have to go in here to make it an equal sign would be the mass. So all the proportionality statement is saying is it's saying that the one variable is equal to the other variable so long as you substitute some constant value into that equation. So let's get to Newton's second law. It says this: if the net external force on an object is not 0, the object will accelerate in the direction of the net external force. If it is 0, we know it's going to be at rest and stay at rest, or at uniform velocity and stay at uniform velocity. But as soon as it's not 0, we're going to have acceleration in the direction of that non-zero force. Another way to say that in terms of the proportionality that we just looked at is that the magnitude of the acceleration is directly proportional to the magnitude and inversely proportional to the mass of the object. That's what we found in the first experiment and the second experiment, where I didn't show you the graph of, but we concluded that A is inversely proportional to 1 over the mass if the force is constant. All right, let's go and look at a few examples. Note that when you're close to Earth's surface, this net force equals ma becomes the force of gravity is mass times acceleration due to gravity, as we've seen before. So let's keep those equations handy right at the top there as well. The first question says a puck of mass 0.151 kilograms has a net force of 15 newtons west exerted on it. What will the puck's acceleration be? And so again, these should be relatively straightforward as we get used to them. But we're still going to go through the process of writing our givens and required and everything on the left side, and then our analysis, solution, and statement on the right side. So our givens, we know that the mass of the puck is 0.151 kilograms. We know that the net force that's being exerted on that puck is 15 newtons west. Now the puck may have other forces on it. We're not going to worry about them. We just care about the net force for these calculations. The acceleration is what we're trying to find. And we know this is the most common version of the equation we'll use. We know that the net force is mass times acceleration. So you could start with the equation on the left, but the equation you're going to be given is this one. And so rearranging that, we just divide both sides by m, and that would give you acceleration. So acceleration is the net force, F net, 15 newtons west, divided by the mass of 0.151 kilograms. And we get an acceleration 99 meters per second squared west. So we've done givens, required. Our analysis was getting the equation. We rearranged the equation and got a solution. And then we are going to conclude with a statement. Therefore, the puck will accelerate at 99 meters per second squared. Apparently my pen is accelerating all over the page. Accelerate at 99 meters per second squared west. You hockey fans who know your history out there, make a connection. Yes, I gave that answer on purpose, so think about why I did that. All right, example B. It's Wayne Gretzky, if you were wondering. Example B says a net force of 2.4 times 10 to the 3 newtons east applied to a car increases its velocity from 6 meters per second east to 22 meters per second east in 4.8 seconds. What is the mass of the car? So you look at this and you say, well, hold up a second. You got time, you got velocities. That doesn't have anything to do with acceleration, mass, and F net. Well, let's see. We have to do some analysis to actually figure out how it does. But it does, I promise you. So let's see. What we're given here is that the net force is equal to 2.4 times 10 to the 3 newtons east. We also know that the initial velocity is 6 meters per second east. And we know the final velocity, not squared, 6 meters per second east. We know the final velocity is 22 meters per second east. So last thing that we know is that the time is 4.8 seconds. We are required to find the mass of the car. And this kind of math is actually something that's not necessarily this particular equation, but maybe for a different variable than what we've got here. This is what different investigators will do to try to, using some physics, to figure out what actually happened in an accident. So we now do some analysis. Well, we know F net. We need to know acceleration in order to find the mass. Well, we know F net is equal to mass times acceleration. But we also should know, and remember from our last unit, that acceleration is the change in velocity divided by the change in time. In other words, it's v final minus v initial divided by the change in time. And so you could solve the acceleration separately and then sub it in, or we could start getting comfortable with subbing two equations together, and that's what I'm going to do here. So I'm going to replace acceleration with v final minus v initial over the change in time. Now, I still am not solving yet for the mass, so I have to rearrange this. So I'm going to divide both sides by v final minus v initial over the change in time. Whatever I do to one side, I have to do the other. And that's going to cancel out that whole fraction on that side, and so I'm left with mass is equal to this. I substitute my known values in. I divide by v final minus v initial. Make sure you do that in brackets. So it's 22 meters per second east minus 6.0 meters per second east. and I'm going to divide that by 4.8 seconds. And so I encourage you to try that yourself to make sure that works. And you might even go 22 minus 6, which is 16, divide that by 4.8. And so you might come to something like this. You might say it's 2.4 times 10 to the 3 newtons east, divided by this 3.33 repeated, and this is going to give you meters per second divided by seconds. So it's going to meters per second, so it's meters per second squared east. And so your easts are going to cancel out, and you're going to be left with units of kilograms. So 2.4 times 10 to the 3 divided by 3.33 repeated is 720 kilograms. So the mass of this car is 720 kilograms. And so you always want to ask yourself, does that make sense? Well, it's probably a small car, but it should make sense. It's in about the right range. So then we've done the analysis, we've done the solution, our statements. Therefore, the car's mass is 720 kilograms. And we've now finished up that with writing the statement. So I want to see that in your homework as you work through things. I'll be checking homework on a regular basis if you're in my class. And I encourage you, work through this, keep practicing this. Don't take it for granted that you know how to do it, because there's always a question that seems to stump some people if you just kind of cruise through. So all the best as you practice that yourself.